Alright, so this is more examples of that special logarithm rule. So again, I have a fraction. There is no quotient rule for antiderivatives. So either I can manipulate it algebraically to get rid of the quotient, or it's our special log rule. Alright, in this case it's our special log rule, which again, you have to recognize, I look at the denominator, let that be f of x. Alright, 3x plus 5. I find the derivative of that. Well, the derivative of 3x is 3, the 5 will 0 out, and so it does check. It is the derivative up top of the function in the bottom. And so as soon as I can recognize that it's that ratio, well, the only rule that works is the logarithm. And so it's the natural log. And then you do have to remember it's the absolute value. Because I can plug negative numbers into this, right? I could plug f of negative 1, right, gives me a negative number, or like f of negative 10, right? I get negative 30 plus 5, which will give me out negative 25. Well, natural log of negative 25 doesn't exist, but the original function does. And so you have to put absolute values so that the antiderivative exists for the entire original function. All right, so absolute value of the function 3x plus 5. And then don't forget to tack on your constant. All right, the next example, we actually have to do a little bit more work in this. This is one of those cases where I actually have to manipulate it a little bit algebraically to get what I want. All right, so first, the bottom function is x squared minus 3x plus 4. The top function is 4x minus 6. So if I take the derivative of the bottom function, I get 2x minus 3. Well, I don't quite have what I want, but I can do something to get what I want, right? I don't need a 4x minus 6, I need a 2x minus 3. But what can I do? Well, if you'll notice, I can pull a 2 out, right? If I divide 4 by 2 and 6 by 2. And again, I don't just randomly divide it, I factor it out. I'm factoring out, I'm going to pull it out to the front. And so what I'm going to do is, well, I'm going to factor the 2 out. When I factor the 2 out, I get 2x minus 3, still divided by the x squared minus 3x. 4 with respect to x. So the 2 is important. It doesn't disappear. But what happens is it's a constant multiplier. So I have a 2. Up top, now I have the derivative that I want of the bottom function that I want. Right? And so what happens is this 2 is just an extra. It doesn't disappear. It's a part of the original function, but it's a constant multiplier, meaning it's just like 10 times x, the 10 will come along, I take the antiderivative of x, which would be x squared divided by 2, and so I get a 5x squared. Same thing here. I'm going to get a 2 natural log of my absolute value of f of x. And so you can't forget the 2, though. It's really easy. A lot of times students will factor out the 2 and then ignore it. But the 2 is a part of the problem. It's a part of the original expression. You can't ignore it. It's a part of the problem. And so the 2 comes along as a constant multiplier of my antiderivative, which is the natural log of the absolute value of f of x. Plus some c, which, I'll write that out. 2 times the natural log of the absolute value of x squared minus 3x plus 4 plus c. Again, I have to put absolute value because I can get negative numbers from that inside function, and I want it to exist for all numbers. So natural log only exists for positive, so I have to make them positive. Alright, so that's the second example of that special logarithm rule. Alright, then the last is going to be just looking at more examples. And so I'm going to get to that in my last video.